I will begin. Heavenly Father, we thank you for this day. I thank you for the students. Just ask you to bless our work today, Lord. In your name I pray. Amen. All right, so we have started talking about complex integration, and I'm going to continue down that path today. And hopefully, I will at least state a few deeper theorems today. Try to resist the urge to get the projector out right at the start, but we will later use the projector, I think. So let me just get started here. So recall that we have defined, right, we're working with this definition, integral of f of z dz. What's this mean over a curve? So I would say, you know, a nice definition is that the integral of, there's two things I tend to gravitate towards, u plus iv times dx plus I dy. And as a formal heuristic, you can think of this as just multiplying things out. And the integrals I'm writing here are just ordinary garden variety, line integrals from calculus 3, which we would define in the calculus 3 way. But that's the complex. And then, of course, the other way we could do it, of course, would just be, integrate from, say, t naught to t1, f of gamma of t, right, times d gamma dt, dt. And then of course, I spent about the first 20 minutes of last class connecting this with yet another notion, right? So anyway, this is the complex integral, and we're defining it, of course, for a curve, or at least for an arc that can be written as a finite union of smooth curves, right? And the question is, what can we say about this, right? So one of the things we can say is the fundamental theorem of calculus part 1 and the fundamental theorem of calculus part 2. These both have natural analogs for the complex line integral. So one of so FTC 1 basically says what? The integral, say from z naught to z of f of w dw, what is that going to be if I differentiate it with respect to z? F of z, in fact, is true. Yep. So that's one of the things we could prove. Now, of course, that there's some terms and conditions on that I'll project here in a bit, but I don't want to get into the terms and conditions of what I'm saying. FTCs too, I'll actually state a little bit more carefully. So fine print to be announced. Okay. There is some fine print there. On the other hand, if f prime of z is equal to f of z on C, then if C has goes from what? Let's say from z1 to z2. I don't know what C is. Could be all kind of crazy curve, whatever. Starts at z1, ends at z2. Yeah? That could be the curve. And for such a curve, if I have that the derivative of big F is equal to little f, in other words, if big F is a what? Antiderivative of little f, right? Then the integral of f of z dz on that curve is in fact equal to big F of z2 minus big F of z1. So that's the fundamental theorem of calculus part 2, but also true in the complex case. Now, so here's the discussion. We have a couple different viewpoints we can go on. If f prime of z is equal to f of z for z in some domain D, then we say big F is an antiderivative, right? That's the usual calculus speak for it. And in complex variables, sometimes people call it a primitive. But I think maybe I like an even, there's another way we could get at this, right? Another way we could attack this, we could also say, AKA F is a potential function. It's a potential function for f of z dz, yeah? In the sense that df, right, is df dz dz, yeah? And so if that's an antiderivative or primitive, that means that we're looking at big df as f of z dz, yeah? So another way we could look at this is the little function f has an antiderivative or has a primitive if the form f of z dz is exact, right? So f having an antiderivative on D is interchangeable with f of z dz being an exact form, right, on D, right? Again, D being a domain. But what else did we learn? We've discussed some theorems there, right? If D is simply connected, right? Or if certainly in the notes, if you look in the notes, there's a proof for D being star-shaped, right? I actually have an explicit proof in the notes that if it's closed on star-shaped, that's true if and only if it's exact on star-shaped, right? So this is, we can add another equivalence here, you know, f of z dz is closed. But this comes with some fine print, yeah? This is not generally true. I need to add a condition here, adding D simply connected. Okay? If in addition we know that D is simply connected, then f of z dz being an exact form is interchangeable with f of z dz being a closed form. What does closed form mean? Remember, that meant if we write f of z dz equal to p dx plus q dy, we have that qx is equal to py, yeah? In other words, you satisfy the condition that's needed to make the area integral in Green's theorem vanish. Or equivalently, the exterior derivative of the differential form f of z dz is 0. That's the closed condition. So we have these different viewpoints, yeah? And they each have their merit. So, but this is very nice, right? I mean, this means that we essentially can do complex line integrals much the same way we did calculus 1, right? So, for example, if let's look at the slit complex plane, right? And if I look at dz over z, right? dz over z for the slit complex plane, I can write that, what's the antiderivative of 1 over z? In fact, it's the principal logarithm, right? This is actually the differential of just plain old log z. So I could do things like I could integrate over an arc just in terms of the endpoints. And so I think this is an instructive example. So I'll set it up here. So we could look like a circle, almost a circle, all right? So it's like a circle it's almost a circle, but it's ending at, let's say, minus r plus I epsilon and minus r minus I epsilon, right? Where this epsilon is greater than 0, right? We could do the integral along this arc, and let's make it counterclockwise, yeah? Let's see, counterclockwise. So we're going this way, right? Oh well, I tried. So then FTC part 2, what's it say? It says that if I call this curve, say, C epsilon, right? Then the integral along this epsilon curve of dz over z, what's it equal to? That's equal to the integral along the epsilon curve of the differential of the logarithm, yeah? So if you look at FTC2, what it really says is if you're integrating the total differential of a complex function, you just evaluate the function at the endpoints. Provided that, I mean, what do we need? We need that the function's actually defined on the whole curve, right? Like you can't just ignore where the function's not defined and hope it doesn't hurt you. Just like you can't integrate, just like our discussion of improper integrals in calculus, right? You had to be careful that your integrand's actually defined over the integration region. That issue is still with us, yeah? So this is just what? Log of, what's my ending point? Minus r plus I epsilon, right? Minus log of minus r minus I epsilon, yeah? Which we can calculate. That's the natural log of the modulus of r squared plus epsilon squared plus I times the argument of minus r plus I epsilon, and then minus the natural log of r squared plus epsilon squared plus I times the principal argument of minus r minus I epsilon. Now for epsilon sufficiently small, actually maybe for epsilon, well no, for epsilon sufficiently small, okay, so fine, it's complicated, right? But approximately, what is this? Let me say this, as we can do this much, as the limit as epsilon goes to 0 from the right of the integral of C epsilon, yeah, dz over z should be equal to what? First of all, these cancel, right? No limit needed there. And how about minus r? You look at these points, you've got minus r plus I epsilon, you got minus r minus I epsilon. What happens as epsilon goes to 0? What's the angle? From the top, we're going to angle what? This is the principal argument. What's principal argument approach from the top of the negative real axis? Yeah, pi. It's pi up here. But as we approach from the bottom, we're swinging right from 0 to minus pi over 2 to minus pi, right? That's where the jump is in the principal argument. So this is what did I just say? Pi. This limits to minus pi, yeah? And I think I have failed to do something, which is what? Parentheses are your friends, right? So that's a minus, which gives me a net of 2 pi I, right? Domains matter, right? You're like, well, the principal logarithm can be defined on the punctured complex plane. That's true, right? This principal logarithm is defined on the punctured complex plane. It's got this angle jump on the negative real axis, right? And this angle jump cannot be ignored because it leads to non-trivial features in integrals, right? That's where the 2 pi I is coming from, that discontinuity in the logarithm there, yeah? We derived this a really different way last time, right? We just integrated directly from the definition and found the same thing, right? Remember? So this is a rather different approach this time. So, oh, and I should mention that if we, and I probably should get the slides out, but before I forget, comment. we could actually define the logarithm. We could define log z as the integral from 1 to z of dz over z. If you believe FTC 1, you see that this has to be true, right? And this is for z in the slit complex plane, right? I mean, I guess you could extend past that, but I mean, I think you could still integrate to, I'm not sure what happens on the discontinuity, actually, right off the top of my head. But this much is true. If we differentiate log z, right? Excuse me, if we integrate this, if we differentiate the formula I just wrote down here, right? By FTC1, we get 1 over z, right? On the other hand, if you differentiate the logarithm as we've defined it before, which was what? What was our previous definition? Our previous definition, which is a fine definition, was this, right? What happens when you what happens when we calculated the derivative of this, right? We also found it was what? 1 over z, yeah? So both the integral and that function both have derivative 1 over z. If you take the difference of the integral and the function, what do you get? You get a function whose derivative is 0, right? On the entire slit complex plane, consequently must be constant on the slit complex plane, which then gives you equality of these two different definitions of the logarithm. So the integral definition has its merits, but obviously, why didn't I define the logarithm this way earlier in the course? The answer to that is pretty obvious, right? Did we have an integral to work with earlier in the course? No, so we had to do this, yeah? Okay. So moving along here, that's one thing I wanted to share with you. And I guess I should prove FTC too, but I think I'm going to project those in a second here. Yes, that's all. I will project the proofs today. Cauchy's theorem. What does Cauchy's theorem say? So just to give you a, while I'm deciding where to erase, maybe we're here. Cauchy's theorem, ooh, what, have I learned nothing? Cauchy's theorem is perhaps a little bit surprising. And you should bear in mind here that this is the first of several theorems of Cauchy. All right, so be careful to be precise in the terminology. I'm showing you Cauchy's theorem right now. There is also, sometimes this is also called Cauchy's integral theorem, which is not to be confused with Cauchy's integral formula, that's a different one, or Cauchy's generalized integral formula, also a different one, although Cauchy's integral formula, special case of Cauchy's generalized integral formula. So that, at least that has, the terminology has, it's not cruel, yeah? But this is Cauchy's theorem, and it's quite beautiful. Let D be bounded domain. Bounded domain with piecewise smooth boundary. All right. If f of z is holomorphic and continuously differentiable, on D, and extends continuously to the boundary of D, then this is, man, so many words for this very anticlimactic end comment, but here it is. The integral over the boundary of D of f of z dz is equal to 0. So this is theorem 9.3.2 in my notes, guys. So chapter 9 in the notes is essentially, the central basic theorems of complex integral calculus. And, this is the bedrock theorem, this one. I've already shared with you the ones that are more or less operationally analogous to the ones we've already seen in Calculus 3, right? So we're starting to get into the theorems that are genuinely complex analytic, all right? So I've assumed continuously differentiable in this theorem. At the end of chapter 9, we will learn something called Gauss's theorem. And Gauss's theorem will say that doesn't need to be assumed. Gauss's theorem is going to tell us that, in fact, if f is complex differentiable on D, which is to say it's holomorphic, that implies that the derivative is continuous. And that's a subtle technical result, but that's the end of chapter 9. But anyway, we're at the start, so we're going to assume continuously differentiable here. My comment to you is that is just necessary for the purpose of our proof right now. Okay? You could strip that assumption off later because it could be added with Gauss's theorem. All right, so the proof of this is, there's a proof in my notes which is based on the full force of the chapter 8 arguments about closed and exact forms. And that proof is good, and you should think through it. But I want to show you a standalone proof because I think that everybody should see this proof because it's simple, beautiful, and it can be easily understood. So the proof is this. The integral over the boundary of D. So I'm going to assume that f is, holomorphic and continuously differentiable, and it has component functions, as usual, u plus iv. All right, f is u plus iv. So this can be rewritten, u plus iv, times dx plus I dy. I'm just writing that down, so this is just you don't even really have to write this down, right? In fact, let me just put that off to the side because I don't have to write that down. This is just a mnemonic for me to remember. Okay, guys? I mean, the definition is what I'm going to write over here. This isn't a step, right? This is just the definition. U dx minus v dy plus I v dx plus u dy. Yeah. And then, all right, so it's a bounded domain. Oh, well, then the Green's theorem applies. Yeah. Now I'm going to use. You're like, well, you didn't say it was simply connected. That's true, I didn't. But do you know what Green's theorem says? If you don't have, like, what's Green's theorem with holes? How's that work? Right? If this is C out, and we have holes like C1, C2, C3. What if you had a Swiss cheese looking kind of shape? How would Green's theorem work on this sort of thing? Do you guys know? No, because I can't deform a loop. These are holes. I'm stuck. Yeah. So Green's theorem still looks the same. In other words, that p dx plus q dy over d, the boundary of D, is equal to the area integral over D of, well, qx minus py dA. This is still true. The issue is the interpretation of the boundary of D. What's that mean? You have to positively orient it. So the outer boundary has to be given a clockwise orientation. All right, which is, so this boundary out here has to go like that. But inner boundaries have to be given a clockwise orientation because that gives them, if you were to walk around the inner boundary, this thing would be on your left if you go that way. And with that adjustment to what we mean by the boundary of D, Green's theorem holds for things with holes. All right, this is the holy Green theorem. Sorry. I should say I shouldn't say that here, but I probably really shouldn't say that anywhere. But anyway. So that applies to this context. If it's a bounded domain, we can apply Green's theorem with holes to that, which means that this can be written as what? Integral over d of, what is this? This is my p, this is my q, yeah? So we've got what? Minus partial x of minus v, yeah? Minus partial y of u dA plus I integral over d. And over here, this is my p and that is my q, yeah? In the Green's theorem, yeah? So I'm supposed to take partial x of u minus partial y of v dA. Yeah?
What does it mean to integrate f of z over the boundary of d if the boundary of d is not a curve? Like if you're here in the old example, it's multiple curves, right?
We add over each curve. We have a curve which is, if the curve, quote unquote, is disconnected, then it's understood to be the sum of the integrals over the disconnected components of the curve, as is the case with that boundary. Yeah. Good question. Great. So what are we looking at here? This is minus Vx, right? Minus Uy. Over here, we're looking at a Ux minus Vy. Remember, f of z is holomorphic, which means what about partial derivatives of u and v do we know? They satisfy the Cauchy-Riemann equations. What do the Cauchy-Riemann equations say about the things I just wrote in red? How are Vx and Uy related? They're not, no. The Vx and Uy, those are the negatives. But you're right about these. Ux is equal to Vy. In other words, 0 and 0. So 0. And that's Cauchy's theorem. So it's not often that I get to the end of a central theorem of integral calculus in this course on a Monday, Wednesday, Friday class ago. And this would be a reasonable thing to ask on the next test. But in this case, yes, this would be a reasonable test question, wouldn't it? I can't always say that. Now, where did I use continuously differentiable? See, that's the fine print that's needed to apply Green's theorem on a bounded region. We do need that the vector field that we're integrating is continuously differentiable. That condition is needed because you're taking partial derivatives of the vector field and you're assuming that those are continuous as well, which is continuous differentiability. So certainly Green's theorem is true for continuously differentiable things. Maybe it's true in a weaker context than that. I don't know. All right, so that's Cauchy's theorem. I have an example of, so I stated this last time I wanted to take a minute or two just to talk about the proof with you guys in class. So for an integral, a complex integral, if the integrand is bounded by m, the modulus of it, of course, then this notation means that z is in the image of gamma. So we call that the trace in my notes following Gamelin. Then the ML theorem says that the value of the integral is bounded by that bound times the length of the integration curve. And so the proof of that is utterly simple using definition 1. So we're looking, like, we take the limit as n goes to infinity, that calculates the line integral, right? That's the definition integral of f of z dz over c is this, as n goes to infinity. But if you just apply it to a finite sum, calculate the modulus, well then the triangle inequality says that, right? But then the norm over the complex numbers is multiplicative. So you just have norm of, length of that times length of that. But this is bounded by m, right? So we get this is less than or equal to, oh, typo, sorry about that. Less than or equal to m times that. Pull the m out, what's this? If you take j equals 1 to n of that, well, that's an approximation of the arc length. And the limit, as n goes to infinity, this becomes the arc length, and that's the proof. So that's, so in other words, to prove the ML theorem from definition 1, it's essentially triangle inequality, multiplicity of the norm, and just take the limit and identify what you're looking at. One of the things is the arc length, and the other is m. And that's the ML theorem. Now you're like, well, that's lovely. And much like Cauchy's theorem, you might not think that's calculationally that useful, but in fact, it is really, really useful. Here's the alternate proof that I will skip. Here's an example. Suppose we're looking at the half circle, radius r going from r to minus r on the r-axis, right? So it's like this guy, right? We're going to try to find a bound on the integration without actually doing it, right? So you have to find an inequality that holds for the integrand. And so here's some new tricks for you guys, maybe. If we want to make this smaller than that, what do I need to do to the denominator? I need to make it, I'm trying to make the whole thing larger, rather. So I need to make the denominator smaller, right? And so here's something that's true. You can take the norm of z squared minus 6, the norm of 6, and the modulus of all that, the norm of all that, or absolute value, if you like. But on the other hand, since we're on the curve of radius r, what's the norm of z? It's exactly r. That's the condition. Norm, modulus of z equals to r puts you on the curve that's a circle with radius r. So this is exactly r. And we have then that this serves as a quote-unquote m, a bound for the integrand over that half circle. And so we can apply the ML theorem. What's the arc length of a half circle? Well, it's pi r, right? And so the ML estimate gives that the integral over the half circle of dz over z squared plus 6 is less than or equal to pi r over r squared minus 6. This is very important towards the end of the course because we like to take these half circles and let the limit of the radius go to infinity. And it's clear as the radius goes to infinity, this goes to 0. So this ML theorem is actually pretty important to our larger storyline in here. Here's the proof of FTC2 I was talking about. To prove FTC2, assume that f has an antiderivative, right, which is df dz, df dz. But because we're talking about complex differentiable, that means that that's partial f partial x. And that's, what is that? That's minus I partial f partial y, all right? And then minus I times minus I gives me plus 1, which gives me this, but that's the total differential of f. And then we're back to the stuff I talked about, like the lecture before that unpleasantness happened. Or maybe before that, I don't know. Anyway, at some point I talked about this is equal to that. That's just the chapter 8 stuff. And there you go, that's FTC2. FTC1, please read the notes. I do my best to communicate important points in here, but there's only so much I can say in class, and there's a lot more in the notes to learn and to correct. Sorry. Anyway, so here's the fine print. Let D be star-shaped, and let F be holomorphic on D. Then F of Z has a primitive, unique up to an additive constant. And the primitive is given by this. In other words, if I have if I can differentiate it, I can integrate it, is what I'm saying. That's kind of weird, isn't it? If I can differentiate it, I can integrate it. That's not what we usually say. Well, fine. I guess if we have continuous function, we can integrate it. So this is a little bit greedier than that in that sense. Anyway, here's the proof. So the idea is simply to use this theorem from chapter 8, which said that if it's closed on star shape, then it's exact. And So we look at f plus uiv, which is this, which is that. It gives me this p and this q. I want to show that this is a closed form, so I just need to show that qx is equal to py. And the reason that that's true, again, Cauchy-Riemann equations, this and that, and that and that. Right? So Cauchy-Riemann equations implies that that's a closed form. Consequently, being star-shaped, it's exact. And the proof of theorem 8.210 said that you build the potential form by integrating the closed form in this way, and that gives you the potential function. And this is exactly why I wrote down the integral definition of logarithm at the start of class today. It's just an application of this construction. So, all right. Now, I think on my schedule I was supposed to talk about Morera's theorem today. We talked about Cauchy's theorem. I'm going to come back and talk about Morera's theorem. And so like next class I probably will, next class I will just project next class. Otherwise we'll be on these theorems for weeks on end. And at the end of it, I don't really want to test you on the proof of these theorems in a test because we're on a Monday, Wednesday, Friday class, and there just is not time to do justice to the proof of any of these theorems in class. But you should see the proofs, though. This is Cauchy's integral formula. That's the next interesting thing on our plate. And this is a really, really weird result. Look at that. The value of f at z is equal to the integral of f divided by w minus z over... What on earth kind of crazy formula is that? That's what we're going to next. So I promise it's going to stop looking like just calculus 3 with like a little bit of window dressing. It really gets very, very different pretty soon. Okay? Thanks, guys.